This video is about how to determine what a molecule looks like. What it looks like actually determines kind of how it acts. And so today I'm actually making two videos. I've already made the first one, which deals with how to find polarity. You'll understand how to find polarity more effectively if you have some focus or some understanding of what molecules look like. So I've put this link on the website, and it deals with shapes of molecules. So we'll open it up. And it's going to look like this when you open it. You're going to have a model choice, and you're going to have real molecules. We're going to look at the model first. So here are three atoms. Should be able to move these around. It's kind of fun to do that. But you can click out here, and they go into their natural shape. So you notice that these guys, see how far apart they are? They want to get as far apart as possible because they are negatively charged, because each one of these lines represents 2 electrons. Now, if I was to put a pair of electrons around there, what happens? See, they pushed them down that way because now we've got repulsion going on here and here. If I put another lone pair on, then it bends them together a little bit more. I don't know if you noticed or not, but watch when I take and put it back in this direction. Now, if I could do this, temporarily it gets out of whack, but it goes back like it was. So if I take away one of those pairs, watch this angle here. So see how it's spread out just a little bit? And the reason it spreads out just a little bit is because now there's not as much repulsion pushing them down as there was when there were 2 pairs. So if I put another one in, it smushes things together a little bit more. If I put still another one in, oh, now look what happens. This is the maximum displacement that they can get to. If I did this, it goes into that shape. So what happens is, the electrons in the bonds and the unshared pairs, they want to get as far apart as they possibly can. If I look at the bond angles, that's 180 degrees, that one right there. And if I put an atom in there instead of a lone pair, so take this out, take one of those out, put an atom in, so that recalculated the bond angle. So those are about 90 at that point. And then if I take another lone pair out, and put another atom in. Let's take this one out and put in a couple of these. Oops, put in that one and that one. So now recalculate, that's where we were. Now I put another one in and take off one of the lone pairs. And now you can see we've got 90s and 120s. So it's 90 degrees between here, get it better, between here and here. But it's 120 between here and here. All right, so you can play with this. I want you to develop a feeling of a chart that I'm going to show you momentarily. So I'm going to take away everything that we have in here right now. And this is where we started. So right now we have 2 places that the electrons are living in this molecule. In chemistry, we call those the electron domains. Okay, so we would say that the electron domains are living in 2 places. There are 2 domains. So going back to our web page, I made this little chart, not that one, this one. This is a bonding chart. It shows, see domains around the center atom. So if you have 2, we say that that is a linear molecule. Let's look back at the picture. Doesn't that look like a linear molecule? And so the electron geometry we would say is linear. And the molecular geometry we'd also say is linear. Now let's suppose I put another atom, I'd have 3 domains. So you have 3 domains right there. All right, so what that does is changes our molecular geometry, what's called trigonal planar. And the electron geometry also is trigonal planar. So if you go back and look at my little chart, if you have 3 domains, the electron geometry is trigonal planar. And the molecular geometry could be bent, or it could be trigonal planar. Now the one I'm showing you is trigonal planar. But if I take this over here like this, we can see. Get them so we can see both. So if I take out one of the atoms and put in a lone pair instead, and then I'm going to take this one out and put in a double bond. let's see, what am I going to take this one out and put in this. All right, so there we have about a 120. And that's one of the molecules that we drew earlier, or you'll see drawn when we're working on a polarity. I drew it right there. So this is a bent molecule. Okay, now why do we call it bent? Well, if you look at just the electron geometry, these electrons, there's 3 domains. See, there's a domain here, and a domain here, and a domain here. So you go over here, 3 domains. We call that trigonal planar. But the molecule geometry, it has 2 that are shared pairs and 1 unshared pair. Here they are, shared, shared, unshared. This actually is 4 electrons, but it counts as 1 domain because they're living in the same area. It's kind of like they're in a more crowded apartment. So 3 domains. So the molecular geometry will be bent. All right, so let's go take a look now at, let's take away the double bond and put 4 bonds, whoops, don't want to do that, put that back, and put 4 of these on and no lone pairs. All right, so you see what happened there? It went into 3 dimensions. And I have 4 domains. So if there's 4 domains, go over here, it's tetrahedral. Now the reason it's called tetrahedral because if you made an imaginary side between here, here, and here, made a little flat triangle, then you turn it and you make another imaginary side over here, and 1 on the bottom and 1 back behind, you'll end up with 4 sides. So this is a 3-dimensional, 4-sided figure. It's called a tetrahedron. All right, now if I take away one of these and instead put a lone pair on, then you get what's called a pyramid. So you've still got 4 domains, you see them? 1, 2, 3, 4. But that 4 domains, the electron geometry is called tetrahedral. See it down here? But the molecular geometry with 3 shared and 1 unshared is called a pyramid. And so this is called a pyramidal or a pyramidal molecule. All right, so let's get a little more complicated. We'll go, what if we had, well, actually, before I do that, let's take this guy off and put on another lone pair. This is what a water molecule would look like. Okay, so water is bent like this because of these 2 unshared pairs. And we say it's still a tetrahedral molecule because it's still got 4 domains. See, 1, 2, 3, 4. But the molecule is considered to be bent. It's a bent molecule. And it will be a very polar molecule because of that. All right. So I think I've kind of laid the groundwork well enough that you can identify shapes of molecules. Let's do one more of these. So I take away the lone pairs. There's my straight again. I'm going to put on some more of these. So now I've got 5 domains. So 5 domains is called trigonal bipyramidal. So if you look at this, you'd have a little pyramid on the top, put a side there and a side on this in the front, a side back behind, so you get a trigonal bipyramidal molecule because it's bipyramidal because there's 1 on top and 1 on the bottom. And it's trigonal because it's triangular. All right, now if you take one of those away and put on a lone pair in its place, now you have what's called, we commonly call this a seesaw shape. So it kind of acts like a seesaw. Okay, so that's 5 domains. And you have 4 shared and 1 unshared. I'm working backwards here, going up. But I tell you what, you can play with this. And let me go back now to the real molecules. So this one is water. And you can see these other molecules exist here. You can pull them up and look at them. SF4, so that's one of those seesaws. See it? In reality, it would kind of look like that. Molecular geometry would be trigonal bipyramidal because there's 5 domains. Molecular geometry is seesaw. All right, if you look at the bond angles, since that's an unshared pair of electrons, it actually pushes these down just a little bit so they're not quite 90 degrees. Okay, I'll let you play with that. I want you to get good at identifying molecular shapes. Now let's take a look at a couple I didn't do over here. Let's just do CO2. So C has 4 valence electrons. We're going to draw a dot diagram for it using the rules that I showed you in the video that I made previously. I'll remind you where that video is. So you come back here. Down here I made instructions for drawing dot diagrams. And I set up several rules for drawing the diagrams. So I'll move it further in the video, even further in the video. Prepare. And that gives us 16 dots to put in. Okay. So even further in the video. And we'll stop it there. But so review this video about how to draw pictures. In particularly, we're going to be down to rule 6 on this molecule that I'm about to draw for you, so I'll take it over. So if you're 4 electrons short, you add a triple bond or 2 double bonds. All right, remember that, and here we go. So we're going to draw CO2. It's got 4 valence electrons. If you're unsure about why it has 4 valence electrons, you might want to go look at a periodic table, which I thought maybe I had somewhere. I do have one here, so you just click on the periodic table and go there. So carbon has 4 valence electrons in this column. Oxygen has 6 valence electrons because it's right here. But there's 2 atoms of oxygen, so you're going to multiply by 2. So our total valence electrons are 4 plus 6 times 2 equals 16. So then you draw your picture, C, O, O, take away the 4 that are already in the picture because each one of these lines counts as 2 electrons. You will remember from the previous videos. So take away 4, and it gives us 12 dots to put in. 1, 2, 3, 4, 5, 6, and that makes 8 electrons around the oxygen. 1, 2, 3, 4, 5, 6 makes 8 electrons around this oxygen. 6 that are not shared electrons, and then 2 that are shared. So these 2 plus 1, 2, 3, 4, 5, 6 makes 8. But we still need to have 8 electrons around the carbon. So since we don't have 8 electrons around the carbon and we don't have any more dots to put in because I've already used my 12 dots, you have to share more. And the rule said that when you're 4 electrons short, that's when you have to add, whoops, not there, not here, here we go. You're 4 electrons short, you add 2 double bonds or a triple bond. But we don't have a triple bond. Okay, 2 double bonds are better because it makes it more symmetrical. I was trying to find a picture over here, going back to my rules, but I don't see it. So I think this is the most, kind of is obscured down here, but I wanted you to see that rule. So if you're 4 electrons short, you add a triple bond or 2 double bonds and start over. All right, so we're 4 short here. We need 2 here, and we need 2 here. So we're going to have to add 2 double bonds. And then start over. So we had 16 valence electrons. We're going to take away 2, 4, 6, 8. So that gives us 8 electrons to put in the picture. So 1, 2, 3, 4, 5, 6, 7, 8. All right. Now, do we have 8 electrons around everything? 1, 2, 3, 4, 5, 6, 7, 8. Around the carbon, 1, 2, 3, 4, 5, 6, 7, 8. Around the oxygen, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 electrons around all of the atoms in our picture, and that becomes our dot diagram. Now, the picture of that, let's go back to this. So here's a picture of what it would look like. I'm going to go to the model side here, so I'll take that away. I'm going to make 2 double bonds, and I'm going to take away these unshared. Okay, so you see, this is what this C double bond O, C double bond O, O double bond C, double bond O, like that, looks like this. So notice when I flip it up like that, it can't stay that way. I try to bend it. Why doesn't it stay? When I pull it this way, you see the guy goes back in a straight line, and that's because the electrons repel each other. So they want to get as far apart from each other as they possibly can. Like that. All right, now if you go to something like this where you take away your double and add a single and then put a pair of electrons in like that, it can't be straight anymore because this pair of electrons down here messes with its shape. So what you end up with is a molecule with properties that are different than they would be if it was straight. So shapes of molecules determine their properties. So I'll give you some stuff to practice on this, and we'll end this video at this point.